So today's lesson is going to be on power. So let's first start off actually with a definition of power. Power is defined as the rate of change of work. Okay, or in other words of saying it is the rate at which energy is converted from one form to the other, because work is a transfer of energy. Okay, so think of it as going from gravitational potential energy to kinetic. Okay, there must be work that's done in order to do so. So mathematically, anytime we're talking about rate, we know that we are dividing by time, and it's the change in work divided by time. Now, this provides, notice the plural here, equations, because we originally defined as work as a force times a displacement. Okay, force times a change of position. So we could divide that by time. But then if you go back into what we originally defined as velocity, displacement divided by time is our average velocity. So this is actually also force times average velocity in order to get an average power. So units, if we look at this, the unit of force is a Newton, the unit for displacement is a meter, and the unit for time is still seconds. And then we also said that a Newton meter is a joule, so this is really a joule per second. And we define a joule per second as a watt. Okay, and we use the letter capital W for watts. And power is a scalar, meaning it does not have a direction associated with it. And just kind of a little handy fact here, that 1 horsepower, which is another unit for power, is about 746 watts. So let's say we have a little motor, electric motor, that can lift a mass that is 1/5 of a kilogram, so 0.2 kilograms, to the lab tabletop, which is 0.96 meters above the ground. And let's say it takes it 3.25 seconds in order to complete that. So we want to know what the power is. Well, so we know power is force times displacement divided by time. So you have to ask yourself, what force are we lifting, or what force do we have to overcome? And of course, that since we're lifting something up, that force that we're overcoming is the force of gravity. And we calculate the force of gravity, m times g. So that's the force. Now we have a vertical displacement, so I'm going to write it as a change in y, or a change in height, divided by time. And now we can just plug and chug. So we have 0.2 kilograms times 9.8 newtons per kilogram times a vertical height of 0.96 meters, and that is all over 3.25 seconds. So that gets us a power of 0.58 watts, and that's our final answer. So if we look at my Civic, the mass of my Civic is 900 kilograms, and it can go up a 10% incline at 30 meters per second, or the fastest it can go up. If the frictional forces are 1,500 newtons, what is the average force the car must exert on the road to move at this speed? So if we start with a little diagram, we have a car here, and it has a downward force of gravity. It has a perpendicular normal force. And if it's going up the ramp, then the frictional force must go down the ramp. And we know the frictional force is 1,500. So if I do this in another color here, we have two other forces that we've typically talked about when we're talking about ramps. The weight that is parallel to the ramp, and the weight that's perpendicular. Because the reason that this is important is if you notice that this weight parallel down here, that part is going down. So in order for the car to be moving up the ramp, okay, there must be an applied force, and if it's keeping this 30 meters per second, in other words, constant, that this applied force that the car is pushing on the ground, and hence the ground is pushing on it, is got to be equal to that weight parallel plus that frictional force. So let's write this out. If it's going up at a constant speed, then we know the sum of the forces is 0. We have an applied force going up, so the applied force is equal to the weight parallel going down plus the frictional force going down. And if you remember how to calculate that weight parallel, it is mg times sine of the angle plus the frictional force. And if you plug in the numbers, we have 900 times 9.8 times sine of 10 degrees plus the 1500. And if you work this out, I got 3010, the 3 sig figs, and that's newtons. So what is my average power output? Well, power is equal to work divided by time, which is force, times displacement divided by time, which is equal to force times velocity. So since I know the velocity, I know the force, I'm just going to use this last part. It's 3010 newtons times my 30 meters per second. And that gets me a power to 2 sig figs of 91,000 watts. Now, that's typically not how power is expressed for cars. Cars typically have a power rating in horsepower. So if I put watts down below and horsepower up above, and I look at the conversion factor up here, 1 horsepower is 746 watts. If I put a 746 next to the watts and a 1 next to the horsepower, I could take my 91,000 and divide it by 746. The watts cancel out, and I get 122 horsepower, which sounds about right for a car of my size. Mr. Sita recently was looking at buying a 15 milliwatt green laser. So that is the power, 15, and that is milliwatts. So if I convert that to watts, any type of milli, there's 1,000 milliwatts in 1 watt. So the milliwatts cancel out, and I get a power of 0.015 watts. So we're trying to look for energy. Okay, well, what we can find is the how much energy is transferred, so that's the work, so that's going to be what we're looking for, and the time is 2 minutes, but of course we don't want minutes, we want that in seconds, so that's 120 seconds. So this is power equals work over time, cross multiply, power times time equals work, and that is a 0.015 watts times the 120 seconds. And that gets us a transfer of energy of 1.8 joules. So that's all for now. Remember that power, we define it as the rate at which a change in work happens. In other words, that you can transfer energy, but how quickly you transfer energy, that will determine your power. Power and energy are not the same thing. They are related by the time variable. Okay, so that's all for now. Have a good night, and we'll talk to you tomorrow. Bye-bye.